Welcome to week 7 live session of quantum chemistry of atoms and molecules live discussion sessions. So in these discussion sessions we generally discuss the lecture notes of the NPTEL course quantum chemistry of atoms and molecules, and we try to solve the assignment problems and some more numerical problems so that can help you in the examination purpose. I am Marco Prabhu Chaudhuri, PMRF at the Department of Chemistry, IIT Bombay. I serve as a PMRF TA here, my teaching assistantship towards this live discussion session. So mainly what we do is, as I told you, that we try to solve the assignment problems in the from the NPTEL program that is there in the SWAYAM portal, and we try to clear the doubt if there are any. And these sessions are recorded and will be available on the YouTube, and the links are actually you must have got it from the NPTEL, or you are watching it directly. Anyway, so if you have any doubt, you can post it in the comment section. Anyway, today we are mainly going to discuss the solution of the Schrodinger equation of a hydrogen atom, or you can say hydrogenic atom, mainly one electronic system. So let us start. We will not solve it explicitly. We will just form the Schrodinger equation. We will show you how the Schrodinger equation looks like, and then we will directly give you the solution of the Schrodinger equation. Maybe in an extra class I will try to solve the Schrodinger equation, and maybe in a future class. Let us start. So today mainly we are going to discuss this hydrogen or hydrogenic atom. So hydrogenic atom means one electron system just like hydrogen. Suppose lithium 2 plus or He1 plus, like that. So if we have to start with the Schrodinger equation, then we must have some idea about the Hamiltonian, the total energy operator. And the Hamiltonian here, if you think of a hydrogen atom, then this hydrogen atom is actually consist of nucleus, electron, right? So the energy, the total energy operator Hamiltonian will be the energy part coming from a nucleus, that is kinetic energy of nucleus plus kinetic energy of electron and a potential energy of the atom. So it will mostly looks like the earlier we have used it. Nucleus mass, suppose capital M, minus h square by 2m del square, and it is del n square denotes the it is an del square for nucleus. And how the electron kinetic energy of electron operator will looks like, so I should put a cap there. Now 2m, small m is the mass of the electron, right? And the potential term is actually consist of 1 by 4 pi epsilon 0. Z is the nuclear charge. Ze actually is the nuclear charge of the nucleus, and E is the charge of electron. They are actually, as they are, magnitude is same, but they are as you know that it is electron having a negative charge and nucleus has positive charge. Here we are dealing with the modulus, with the magnitude, and the position of the electron with respect to the nucleus. That is that can be also defined as like this, where Rn is the position vector of the nucleus and Re is the position vector of electron. So this is the potential energy, and as you can see, the potential energy here itself is negative, which means there is a attract potential energy, right? That is why the sign is negative. Anyway, but as you can see, this del n square, if I break it down, then you will see that it consists of del square del xn square plus del 2 del yn2 plus del square del 2 del square and del electron square. That Laplacian of the electron is of a different coordinate, right? So right now we are discussing in this thing in the Cartesian coordinate, but still we will see that there are actually 6 variables there. That is the first problem we face, that it is difficult six variables. So what we will try to do, that we will convert the Hamiltonian into some other coordinate system in the Cartesian coordinate, to be honest, at the first, but to some other means we will convert it to some other coordinates, such that we can get the motion of the entire atom and motion of the electron relative to the nucleus, so that in the later part, when we will be able to do that, we will only be worrying about the motion of the electron with respect to the nucleus, because the whole atom in free space will act as a free particle. So that motion will not be worrying about. I will write what I am trying to say. So by somehow we are trying to make the Hamiltonian the center of mass motion and Hamiltonian of the electron relative to the nucleus. Not only the electron relative to the relative motion of electron with respect to the nucleus. So why? So what I am trying to write is, CM is center of mass coordinate. So as a whole, so this HCM, when it will operate, so that time our wave function psi total will be a product of psi center of motion and psi electron. Let us write psi relative. So this HCM, when it will work on psi CM, it will give us some energy, and this psi CM back, these are all. So this energy is actually going to be translational energy of the hydrogen atom as a whole, means both nucleus plus electron, because it is coming as a treatment due to the center of mass motion. And you, when we get so this actually will give us the relative energy of the electron only with respect to nucleus. That is why it is relative energy. So, so your nucleus, so your electron is actually rotating around. I should not say it in a proper sense, but your electron is moving, your nucleus is moving. Your electron is moving around the nucleus, and your nucleus is also having some motion. But as a whole, if you see, your now nucleus and electron both are moving in space. So that uh, hydrogen atom itself is acting as a free particle where there is no external potential energy. So that kinetic energy is only the translational energy of the hydrogen atom and is not quantized. So we'll not be worrying about that, but what we will be more interested about the relative energy of the electron. And so if we can separate the Hamiltonian like this, then we can work with the Hamiltonian. So this is what we want to do. Now we will transform this. Suppose right now it is in the coordinates of nucleus and electron, and now we will convert it to the coordinate of center of mass and the electron. So first of all, we need to define the position vector of the center of mass. So is something like R. It is usually defined as the mass of a nucleus and the position vector of the nucleus, mass of electron into position vector of the electron divided by the total mass. So this is the position vector of Cm, and the relative motion. So of electron, or you can also say with respect to nucleus. This is not a free electron. This is with respect to nucleus will be small r, that is equals to like what we have already defined it, Re minus Rn. So I will not overwrite this. So this is the position vector. I'll just go to the drive, staying the call. Now these are the position vector of center of mass and position vector of electron. Now we need to define, suppose there as you can see that these here it is del square by del 2 by del xn square. Right now if we want something in del Laplacian of the center of mass, then it will be something, suppose this is r, but the positions are to be, if I have to be precise, then this is, suppose I am going to write r capital X, capital Y, capital Z, and here the coordinates are small x, small y, small g. Okay, now if you see, right now also we have 6 variables, capital X, capital Y, capital Z, small x, small y, small z. Earlier we had xn, yn, zn, xe, ye, zd. We need to interchange between the coordinates. So you may have the question that from 6 coordinates, 6 variables, we are again going to reach to the 6 variables. So what is the benefit? So that is what I told you, that ultimately when we able to do that, your one part of the Hamiltonian will be as a, we can get the translational motion of the hydrogen atom as a whole from there. So we will not be worrying about that. So we can work with rest 3 variables which are related to the relative energy of the electron, which is our interest here. So let me define this. So we will want something like this. These are capital. Now, and what we have is possibly writing it twice, but it will make sense in a few minutes. So we need to convert this. And from these vectors we can actually write it like this. If you think only about the x, or suppose only the magnitude, because we are not worrying about the a unit vectors right now. It is something like xi, yi, zi, right? Xi, yk, xi, yj, zk, where I, j, k are the unit vectors. Right now I'm writing the modulus only, so it will look like sorry, should also mention this. If sorry, if I am only talking about the vectors, then I should not put the modulus. Okay. We cannot do that. So anyway, I will just then cut it like this. I was thinking of erasing it, but I could not do it. Anyway, so it is something like this. And small x is xc minus x. Okay, so I'm not writing explicitly what y or small y looks like. I hope you can understand that the capital Y is myn plus mye by m plus m, and the small y would be ye minus yn, like that. So I will be just doing for one of the dimension, and it will be the same for all the three rest of the two also. So, and at the end we will see what we are getting. So here del by del xn, actually we can write it as, so whenever we need to change the coordinates or the dimensions to interrelated, they are interrelated. How they are interrelated, I will show you. So suppose you need to change it to from del xn to del x and del small x. So we will do it like this. So differentiation with respect to x, differentiation of x with respect to xn, and where our xe is constant, multiply by del x plus del. So this part Professor Datta has not shown explicitly, but he has given in the appendix section. That is why I am trying to highlight it, so that you can learn how that conversion was done. So, and in terms of small x also, so when we are converting these things, then delta xn, obviously x is constant multiplied by delta x. So what we will get from here, if we do a differentiation with respect to xn where x is constant, so we will be getting capital M divided by this delta by del capital X, and here we will actually get negative, right? We negative because this is constant and this is minus 1. We will get, if we do the differentiation, so we will get minus 1 del of del xc. So if we take, we want to get del xn square, so we will get, so we have to do a square of whole, right? So m by m plus m square of that del 2 del capital X2 plus del 2 del small x2 into m by m plus n del x. Achha, I have made one mistake here. So it should be small x. Here also. So this is what and so this is one of the thing we got. And what about del by del xe? If we have to get this, then we can similarly do it by same way, where xn is constant. Now del by del capital X plus small x with respect to del xc, where xn is constant, del by capital A small x. Now this is, if you see now, if I have to do a differentiation with respect to the xe, where xn is constant, now we are in almost similar thing but a little different. So now we'll get plus 1. And what about del square del xc square? So that we will get so that is whole square del square del x square plus 2 small x, this is capital X. See, earlier I had the Hamiltonian as minus h cut square by 2m, where mass of nucleus, delta n square minus h cut square by 2m, delta electron del, not delta, del minus 1 by 4 pi epsilon 0 z square by r, correct? Now, and del n I told you what are there. So if in only if I have to think this in term of only one coordinate, then it looks like something like this. So first I am trying to show you for only one coordinate, and then as all of them yield the same thing, so we can directly write it. And let us take this 1 by 4 pi epsilon naught as q, so that it will be less problematic. Not problematic, you have to write it over and over. That's what I am trying to avoid. Okay. So now if you think about this, then we can put the values what we just got. And the values are m by m plus m whole square, del 2 del x capital X2 plus del 2 del small x2 minus 2 right. And in this case we have small x, and don't forget the potential energy term. So ultimately we'll have something like minus it is square by 2m. Actually I can erase this. We'll have m we'll have h cut square is 2m capital M gone, and in this side we'll have the similar treatment. And this cross term is hopefully going to annihilate, because this cross term will be annihilated, and we will add this del 2 del capital X2 and del 2 del small x2 terms, and that will looks like have your potential energy term. So this and this is gone. So and do have actually missed this two term. Now see, interestingly, here this looks like the whole atom, right? What we were discussing, the center of mass, where it is, or the whole atom, mass of nucleus plus mass of electron. So it is actually the kinetic energy of the center of mass and to only one direction, towards x direction, right? So we were discussing that we are now only doing it for only the x direction, and then y and z will follow the same thing, and so we can write the whole thing. And this we have earlier discussed, right, that 1 by m plus 1 by m means the mass of nucleus and mass of, so this is like a two body problem, and when we can replace this by 1 by mu, and where the mu is the reduced mass, right? Small x2. So now you will see that we have, so I will go to the next page maybe. So this is for one dimension. So for three dimension, what if the same thing follows, then we can write that we are going to get, so we are getting in terms of del 2 del x2 capital X2. So this is for center of mass, right, Laplacian. Then same here we will get 2 mu, and this is the relative coordinate, and the potential energy is going to unhalf, right? So we will not multiply it by 3 because this is going to be unchanged. Is for all three. We should have kept it, maybe I will do that, so that will make much more sense. I will not use it, or maybe no, I should not use it, because you will see that is one of the main problems. I will discuss it. I should not write it here. That is one of my mistakes. So I will discuss why I am doing it, why I am reading it, and also this. So instead of H, I should write only the kinetic energy part, Hamiltonian. I'll write why I am doing it. So ultimately, the overall Hamiltonian we will expect something like this. Where this part is actually your Hamiltonian with respect to center of mass, and this total part is Hamiltonian of your relative motion of the electron with respect to thing. So now you can see we won't be bothered about this part. The Hamiltonian of the center of mass will only be bothered about this part, the relative part, and we'll work the Schrodinger equation. We'll try to solve this. We'll take this Hamiltonian and try to work on the psi relative part. So now we will, so we are able to break it into two terms, that we will right. So the Schrodinger equation will look like this will be our time independent Schrodinger equation for the hydrogen atom. So this is what we are trying to solve. This we will be able to. So far what we have done, we have reduced from six. We were having 6 variables. Now we are having 3 variables with respect to the relative motion part, and that are x, y, and z. So now it seems easy, right? We have already crossed one barrier, but now you will see what I was trying to say. Now this r, if in Cartesian coordinate, this r is nothing but, if I have to take it under denominator, right, as a denominator, it is nothing but 1 by root over x square plus y square plus z square. So for separation of variables, we know we need to, as we have done just before this, so for a separation of variables, we need to take the overall wave function as a product of two, and the Hamiltonian as a sum of two of the variables. But here it will be very tough to break down this Hamiltonian, as this r is in there in the denominator, and this r is nothing but 1 by r is nothing but 1 by root over x square plus y square plus z square. This to separate this thing into the separate addition of 2 terms or 3 terms will be, in terms of x, y, z coordinate, will be very hard. So that is why now we will shift from Cartesian coordinate to the spherical polar coordinate.
दो कॉपी चाहिए, प्रिंट दे रहा हूँ.
One coordinate because separation of Hamiltonian due to separation of Hamiltonian due to this potential energy term is almost impossible in, is hard. Let us not say impossible, is will be harder. But when we will discuss in terms of spherical polar coordinate, that is r theta phi, then we don't have to even bother, because r is the coordinate we want, right? So now till now what we have done, we had the Hamiltonian in terms of nucleus and electron. There are 6 variables due to the 3 coordinates of nucleus and electron each, and from there we have converted it to the Hamiltonian of the center of mass and the relative motion of the electron with respect to the nucleus, and there we have only now focusing on to the relative Hamiltonian of the electron with respect to the nucleus, and we are not bothered by the center of mass motion, because that will act as a free particle in the space. And then from the till now we are in the Cartesian coordinates, and now we are moving from Cartesian coordinate to the spherical polar coordinate. And for that, we have to now what we can do is that we can now show that my psi relative, what we were earlier using, that to be, because now we are going to have three dimension, that is for our spherical polar coordinate r theta phi. So we have to write this psi, not capital, maybe a small psi will also work, as a relative to as a function of r. These are capital theta, function of theta and phi. Okay, and the Hamiltonian or this Laplacian, you can say, this we have earlier idea, right, from the rigid rotor problem, that how this uh, uh, Laplacian will looks like. Let me write it here. It will be something like, so you can also right now it is there in the appendix too, but I am not doing it because then it will be very time taking. You can do the same treatment what we have done for the same, like what I'm trying to say is you can do the same thing, that 1 by del x del x, you can write it in terms of del r, or sorry, possibly del small r by del x, where your theta and phi are constant, then this is your delta by del r plus your del r by, sorry, and you already know that this z equals to r cos theta. These are the polar coordinates. X is r sin theta cos phi, y is r sin theta sin phi. In other terms, your r is x square plus y square plus z square. So I should write here this y as your constant and your theta is cos inverse z by r, and your phi is tan inverse y by x. From there actually you can do it like del r by del x, del theta by del x, because you already know what is r, right? Root over x square plus y square by z square. So it will be actually time take, as sir has also provided already to your appendix 2, but you can so this is one of the equation. Now you can have it in terms of delta y or del by del z, and you can actually by that you can arrive at the Hamiltonian. So I'll write the Hamiltonian directly in spherical polar coordinate, what it will look like. So it is actually, you don't have to remember this. So I am not also, I will not be able to remember it. I am writing it just by looking at my notes. So please don't try to remember it or mark it. If required in the questions, or it will be given. So your Hamiltonian um, sorry for that. Okay, let's get it changed. Okay, so your Hamiltonian in spherical polar coordinate will be looks like minus h cut square by 2 mu. We already know we are dealing with this, and then 1 by r square del by del r square del by del r plus 1 by r square sin theta del by del theta sin theta del by del theta plus 1 by r square sin square theta del 2 del phi 2. So this is your Hamiltonian in spherical polar coordinate. In case of the rigid rotor, we are earlier ignoring the delta del r part, because if you remember that in case of a rigid rotor, we are saying as the r is constant, so del by del r will be anyway 0. So we are not bothered about that radial part in the rigid rotor case, but in the case of hydrogen atom, that part will be required. And the rest of the I will just show you how to get the ultimate Schrodinger equation and separate them out, and from there we'll directly write the solutions. So we'll not get into the deep of it. Okay, so what we are going to do is now H psi is equals to E psi, right? So where you can say this is relative, this is relative, this is relative, and this is also relative, right? So it is minus h cut square by 2 mu 1 by r square del by del r square del by plus 1 by r square sin theta del by del theta sin theta del by del theta plus 1 by r square sin square theta del 2 del phi 2. Okay, I missed one term here. See, so this is the kinetic energy term, right? I missed the potential energy term, which was like this, right? So just like this we can write it. So this multiplied by your psi relative, which is now r capital theta and phi, right? This minus you same with the qz square by r capital theta phi capital phi will be equals to your e relative into your r theta phi, right? Now we'll multiply both sides minus 2 mu r square by h cut. We'll get, and rearranging, del by del r square del by del r plus 1 by sin theta d theta sin theta d theta. Acha, one more thing is that when r theta phi is applied, when you see for the first case only r will be here and theta and phi will act as a constant, right? For this case your r and phi will act as a constant and your capital theta will be here, right? Same, plus here your r and theta will act as a constant. Is del square del capital phi square minus q z square by r capital theta phi, and also you remember we have multiplied it by minus 2 mu r square divided by h cut, and that's why the right hand side will also become negative, so we will take that thing into the left hand side, so it will become positive. That is 2 mu r square by h cut by r capital theta phi will be equals to 0. Now dividing both sides by r theta phi will get 1 by r del r I am doing all this derivation for you because you will get to know the step, and I am not jumping the steps, so that you have a clear idea, and it is very important to have that idea at this point. Why we are, how we are getting the Schrodinger equation or the wave equation for the hydrogen atom or the electron with respect to the nucleus, which is of our interest. See, right now what we are trying to do is the separation of variables, right, into the different r, theta and phi coordinates. So when we will be able to do that, you will be seeing I missed h cut square term here, I guess. Yes, sorry for that. This equals to 0. Now on the next line, when we rearrange this, you will see the first term is only dependent on the r, the small r, capital R, and the second and third is actually have the second part is only dependent on theta, and the third have both from theta and phi. And if you see the potential energy terms which are there earlier, they are mostly, as if you see, they are mostly dependent on the r dependent part. So right now what we can do here, we will separate them out. How? Let's see. We are almost done with the separation of variables, or you can say we are at the first step. This we will put in the left hand side, and the rest of the part we will take into the right hand side. So our left hand side will only be dependent on the r, small r. So you can say this side will be the radial part, and this side will be something like spherical harmonics, which is only dependent on theta and phi. But again we need to separate them out. That we will do in time. See, so the left hand side is only dependent on the radial part, and the right hand side is dependent on theta and phi. So you can say if they are equal, then we can equate them to a constant, right, which will be a dimensionless, because then it can be only equated, right? So that we will do. Okay, so we need more blank slides, so I will arrange them maybe. Today we are mostly doing the derivation part, but not much, I guess. Not much means not much more. So here what we have is 1 by r
American Federalism मध्ये पास आहे
by r del by del r del by del r plus 2 mu r four pi epsilon naught, or as we are taking it as q, z square by h cut square plus 2 mu r square er both of the sides are equal to beta, some constant beta. So what about the right hand side? Right hand side is 1 divided by capital theta sin theta del by del theta sin theta del capital theta by del theta minus 1 by capital phi sin square theta del 2 capital phi del phi 2 is also beta, right? Now see what we can do. We can multiply this equation both sides by sin square theta and rearranging, we'll be able to get to be honest minus sin square theta, suppose we are multiplying it with, so we'll get something like sin theta by capital theta del by del theta sin theta del capital theta by del theta plus 1 by capital phi del square phi del 2 phi, to be honest, minus beta sin square theta, and as I was telling that we'll rearrange it, so maybe okay, let me do it here only. That beta sin square theta is equals to minus 1 by phi del 2 phi del phi 2. See, now in this equation the left hand side is dependent only on theta and right hand side depend only on phi. So again we have the chance to equate both of them to a certain constant and get the theta dependent part and the phi dependent part, right? So if we equate this side to something to minus m square, right? Oh, sorry, to m square. So and this side will become 1 by phi del 2 phi del phi square is equal to minus m square, and eventually that will lead to del 2 phi del phi 2 plus m square capital phi 0. So you can see that now we have three separate equations. Separate equation. This is a radial equation. I should say maybe radial equation, r dependent part. This is your theta dependent part, and this is your phi dependent part. So we are able to separate the variables into the spherical harmonic coordinates, that is r, theta, phi, and I will not try to solve it right now because we are already doing much mathematics yet till now, so we'll try to restrict ourselves to this equation till now, and we can maybe check the solution later. Sorry, the the exact solution, how to do that we'll do it later, but let us actually appreciate the solutions right now directly. So the solution of the phi dependent part that we know, we will get from there, we will get something like phi m, right? So it will be something in terms of m, small m, that is 1 divided by root 2 pi. So this is the solution for the phi dependent part, right? Where m will be 0, plus minus 1, plus minus 2, plus minus 3, like this. Solution of the, and so this gives us the magnetic quantum number. And what information does it give us? So it actually specify the orientation of angular momentum in space. In space, like it will give you mh cross, right? If if you are operating LZ operator on the wave function, then you are going to, or in the phi dependent part, so you are going to get something like m h hat. So in h hat unit, so you are going to get the orientation around the A of the angular momentum in space. And solution of the theta dependent part is little tricky, or I should say have many terms. L minus m. Now you see it's dependent in the theta part, it is dependent on two things, m, modulus of m, and L. M is this magnetic quantum number, and another quantum number or another number has come, as you can see, that is L. That is, I'll come very soon. I'll write this thing up and then we'll discuss what that is. So this is the normalization constant of the theta dependent part, and there is a polynomial that is known as, and that is dependent on not theta but cos theta. So when actually we will try to solve the theta dependent part, then you will be able to see that why it is theta not um, uh, why it is cos theta not theta, that time you will be know. And this p in this polynomial is known as pm in cos theta is known as associated Legendre polynomial, and this actually is given by, so I will give you a separate set of expression, mathematical expression, which is sir has given a little, Professor Datta has given a little different, but I try to prefer this thing, but you can anyway choose in that. So this is 1 by 1 minus cos square theta. I can actually I will, for simplicity I will write z here, 1 minus z square m by 2 to the power m by 2 d modulus of am d z, and this plz. So this L is actually azimuthal quantum number, or you can say orbital angular momentum quantum number, orbital quantum number, which is, so this m can have the value from 0 plus minus 1 m. Actually it has a restriction, that is it is m modulus of m is less than equals to your L, and your L can have finite values 0, 1, 2 like this up to n minus 1. What is n? So I have put this thing early. So this n is actually going to be your principal quantum number, and this actually is a part of your solution of the radial part, that is so this is also something different, expression is different from, a little different mathematically, but says the same thing. So this is multiplied by rho by 2, rho to the power L plus 1 n plus L. Please don't try to mark this thing. I am also looking at my notes and writing this. So where this is another polynomial, this L 12 plus 1 n plus L rho, where rho is your 2 r by n a naught, where if you remember, this a naught is actually going to be your radius of the first Bohr orbit, and it has so when you do the solution, you will see that a0 has it as a separate expression, which we are actually using it to look this expression as a small expression, but it is actually a bigger one than this, and this L12 plus 1, or you can say let us write it like this, SP rho. So this is actually, this has the expression ds by d rho s p of rho, and this lp of rho is e to the power rho d rho dp d rho actually. Let me write it again, maybe I'm confusing you. D rho is d p d rho p rho to the power p e to the power minus rho, where this is known as associated. I am saying many a time that you don't have to mark this thing. This will be given in the question papers. This is just for your information that how the solution looks like and what information we are getting from there. So as you can see, another quantum number, that is n, is your principal quantum number, right? And it can have values from 1 to 3, right? So, and this specify actually what is the means, you can say what is the significance of n here. N actually will be, it will actually give you, specify the energy levels, the energy of electron here, because we are only working with the one electron system, and azimuthal quantum number will give you the magnitude of the total angular momentum. So this is your solution of phi dependent part. This is your solution of theta dependent part. And this is solution of your radial part, or the art dependent part. Okay. So you can see we are getting three quantum numbers from the Schrodinger equation, that are n, l and m, where your radial part is dependent on n and l, your theta dependent part is dependent on l and m, and your phi dependent part is only dependent on m, that is magnetic quantum number, or ms you can say. So, sorry, ml you can say. So three quantum numbers, but you already know from your 10th and 10 plus 2 and your bachelor's degrees and bachelor time that this another quantum number is there, that is your spin quantum numbers, but that spin quantum number doesn't arise from the solution of this Schrodinger equation. That arise due to a different thing, a relativistic uh, solution of that Schrodinger equation, but not from this Schrodinger solution of the Schrodinger equation. So that is a relativistic treatment. From there you can get the spin part, and that spin can be only, S can be only half. Okay, spin is half, and the spin quantum number, that is ms, that is half and minus half. That we will actually discuss in the latter part of the lectures. Maybe in that will be introduced to week 6 or week 7, and that ms has plus half and minus half, that is spin quantum number. Spin can only be half, and that s is associated with the magnitude of the total spin angular momentum, and ms, that quantum number, is will be related to the orientation of the spin of the electron in the space. Okay, and yes, and the other things that are discussed in the lectures are like the radial function. So the how to plot the radial function, that was discussed, like for psi 1 is how this psi 1 is means psi 1 0 0, right? Your 1 is n is 1, l is 0, and as l is 0 you have only m can be 0 only. So that wave function will looks like 1 root over pi 1 by a0 3 by 2 e to the power minus r by a naught. So this is how your psi 1s looks like, and this is, so psi 2s is psi 200, right? So I'm just giving you this equation for expression for now. It is, you don't have to mark it. Obviously it will have the first case, you did not have a polynomial of r, but in this case the exponential term is there. So how does this wave functions looks like if you plot the radial functions look like if you plot them with r? So in the first case it will look something like exponential decay, right, in r. So this is for your 1s, and how will your this 2s will look like? There is an exponential term as well as a polynomial in r. So from there you can see actually that your this function will be have a node, and node will be when it will be equated to 0, this polynomial, and that is r at 2 a0 to a naught. There you will have a node. So it will first have a decay. Maybe it can have different amplitudes. So from there it will come. Sorry for that. So it will come down as an exponential function. So it will come down as exponential function, and then it will asymptotically be 0. So let maybe try once more. So it will not again change the sign. So it has changed. So here it was positive and it is negative, something like that. Change the sign. So your node is at 2a0, right? And then it will be 0 at the infinity. Okay, so this is how your 2a's will look like. So this is how you draw the radial functions. So these are mostly radial function because your theta and phi dependent part are not there, radial functions. And there are another things that are radial distribution functions, or and you can call them also radial probability distribution functions. How it is different from the radial function? So now if you think of this as a radial function, one of the radial function can be r of radial part, or the r this square of the modulus. So this will give you the distribution of your distribution of the probability density, right? Probability density, not the probability. When you will get the probability? When you multiply this thing with your volume element. So probability will be, probability density multiplied by the volume element, right? So that is your d tau, and a square integration over the all space. Here also your d tau is, and this is your radial part. So maybe this is radial probability density, you can say. And then your, actually, if I have to write it in terms of maybe this, psi r theta phi, suppose something like this, square of this all space, then here it will be something r. Your d tau is actually the volume element in spherical coordinate, r square dr sine theta d theta d phi. So it is like this, 0 to r multiplied by your 0 to pi sine theta d theta multiplied by 0 to 2 pi d phi. So if you see, if you don't have a theta or phi dependent part in your wave function, then obviously they are going to become 4 pi, and oh, I missed one part, I am very sorry for that. So this is actually not the theta, right? This should be r squared dr. So eventually, if it is mostly for an s orbital or something like that, if you are going to get something like 4 pi r square like this. So for mostly for s orbitals, and that is going to give you your radial probability distribution function. And how is it different from your radial function or the plot of radial function? As you have already seen, this is your radial function, and from there you can see if you are taking an square of the modulus, then you are going to have two lobes, but still it will looks like your radial probability density, radial not probability, radial probability, yes, radial probability density is maximum at nucleus, but when you are going to draw the this basically r square r modulus of the radial function, then you are going to see that actually it is having something like a maxima at a0 for 1s, and for 2s this lobe will be, first lobe will be smaller, and obviously they are going to have, this is at 2a0, and then it will have a bigger lobe that will something like this. This is here for 2s. I may have drawn it improperly, but this is how it should, means you should get the notion that how it will look. So it will have two lobes, but the maximum won't be at the nucleus, because here you are multiplying with r square, which is an increasing function. So as the r increases, your this product of this is going to get increase at r equals to 0. See, at r equals to 0, this product will have 0. So your probability, radial probability, which is not different from your probability density, is almost 0, almost I should say, or close to 0 at nucleus. So for 1s at a0, how you will get that? So that most probable value of the radius you will get by you first need to get the probability function, and you need to have a differentiation with respect to r and make it 0. So at that point it will have either maxima or minima, and you need to, so inflation point you will get, and you will get your most probable value of your radius. Okay, and some other things I want to also discuss, that from here you can get your number of radial nodes as n minus l minus 1, and angular nodes is the your azimuthal quantum, that is n. And with these actually we can actually move on to your assignment problems. I know the time is, we have at least 15 minutes more, so we will be able to solve the assignment 5 also. So let us do that one by one. So the first question is separation of the time. So these problems will only be based on the thing what we just discussed and what Professor Datta has taught us in the lectures. So let us solve these assignment problems. So the first problem says the separation of the time independent Schrodinger equation for a hydrogen atom into two parts yield the solution or equation of motion of obviously the center of mass. The first option is right. Electron in the elliptical orbits, that's not true. Electron with respect to the nucleus, that is the relative motion of the electrons, that is correct. And a free particle, that is also correct, because your center of mass for the atom or the whole atom as a whole, it will be a free particle, because at space it is not facing any external potential, which is equivalent to a free particle, and the energy will not be quantized, it will be a continuum, and it will give you the energy is equivalent to the translational motion of that atom. So the question number 2 is, it is convenient to write the time independent Schrodinger equation for a hydrogen atom in terms of a spherical polar coordinate, because this coordinate system, it is also a multiple correct answer, as you can see from the squares. Account for spin of the electrons for no, this is not correct. In the Schrodinger equation, spin is not there. Is more suited for a central field problem, it is correct. Leads to the separation of variables, it is also correct. And is the only system which the angular momentum operators can be written on, not really, not the only system, you can use the Cartesian coordinate system. So this is not also true. Question number 3, the constant m discussed in the context of hydrogen atom obviously connect two angular equation, right? In spherical harmonic you have your theta dependent part and the phi dependent part, it connect both. Is related to the total energy, it is not. The total energy is dependent only on the r dependent part, that is the n quantum number. Is related to the total angular momentum, not really, it is related to the z component of the angular momentum. So these two are the correct answer for the question number 3. Now question number 4, the solution of time independent Schrodinger equation of hydrogen atom in spatial coordinates is, see here it is written as spatial coordinates. Spatial coordinates is all the r, theta and phi. So actually it is going to give you your principal quantum number, that is n, your azimuthal quantum number, that is l, and magnetic quantum number, that is your ml or small m. It is not going to give you the spin quantum number. So that will come from a different treatment, relativistic treatment. Okay, now question number 5, the total angular momentum for L equals to 3. So now your total magnitude of the total angular momentum is, when you operate on the spherical harmonic or the total wave function, you are going to get the eigenvalue as L into L plus 1 to the power half, or square root of that, you can say, multiply by h cut. So here for L equals to 3, you are going to have your magnitude as root over 12 h cut, and root 12, if I use a calculator, something around 3.46. So let me write that. So z component of angular momentum, again earlier we get the total magnitude of the total angular momentum. Now the z component of the angular momentum for L equals to 3 and m equals to minus 3. So your that z component is given by actually mh cross. So it is minus 3, it will be, and your unit is h cut, is already in terms of h cut is given, so it is minus 3. Now question number 7, among the following orbital the z component of angular momentum is not defined. See, now this is a very important question. So the z component of angular momentum will not define for those orbitals or those real orbitals like px, py, even for d orbitals x square minus y square, or uh, those orbitals or d x y y z x z, those orbitals, because those are real orbitals which is coming from a linear combination of the atomic orbitals. Suppose here 3px is going to be the answer, right? So 3px is coming from a linear combination of p minus 1 and p plus 1. That is why it is not going to have any z component of angular momentum. So it is not going to be an eigenfunction of the angular momentum LZ operator. So here the answer is C. Actually, in the upcoming slides, I have some questions related, numerical questions related to this hydrogen atom. So today I'll give you the question so that you can and you have the note so that you can try to solve it yourself. And on the next day we'll come and we'll solve it together. So that would be a good exercise. Now question number 8, number of angular nodes for 3p orbital. As I told you, the angular nodes is the number of the L, that is the azimuthal quantum number. So for 3p it is 2, right? So the angular nodes for 3p orbital will be, oh sorry, it will be 1 because p is related to 1, d is related to 2. So angular orbital will be. Then question number 9, the following is the wave function for which orbital. So this is a radial function is plotted. So as you can see, the function has a node, right? So it has only one node, radial node. So radial node is n minus L minus 1 is 1. So n minus L is 2. See, what are the options do we have? We have 1s. For 1s, n is 1, s is 0. So that will be 1. That is not 2. So 1s cannot be a right answer. What about 2s? n is 2, l is 0. So it can be a correct answer. What about 2? 2 minus 1, that is 1. So it can't be a correct answer. What about 3s? For 3s, you can see it is 3 minus 0. So it will be 3. So it is also not a correct answer. So 2s is the only correct answer. Now question number 10, the probability of finding the electron is uniform in every direction in which orbital? So out of this, only s orbital is spherical. So the probability of finding that electron will be uniform only in the s orbitals. Now the question number 11, arrange in the increasing number of radial nodes. So let us calculate for 3p how many radial nodes will be there. 3 is n and p is 1. So 3 minus 1 minus 1, that is 1 node for 3p. For 4s it is 4 minus 0 minus 1, that is 3 nodes. For 1s it is 1 minus 0 minus 1, 0 nodes, 0 radial nodes. 5d it is 5 minus 2 minus 1, that is 2 radial nodes. So in an increasing manner, so the least is 1s, then it will be 3p, then it will be 5d, and then it is 4s. So third option is the correct answer. I think this is the last question for these assignment problems, but let me give you some more numerical questions. Actually these questions are prepared by the faculty members of Department of Chemistry, IIT Bombay, for a quantum chemistry first year BSc quantum course, and I acknowledge them for providing me the questions so that I can share it with you and we can solve it for your understanding. So please try to solve these questions before coming to the next session so that we can have a good interactive session. And if you solve these questions, you are actually going to have a better idea about the and you have a better concept. So see, in this question you will have to, from these orbitals or the projections of the hydrogenic orbitals, you need to find out the quantum numbers n and l. How can you do that? You need to check how many angular or radial nodes they have, and from there you can guess the n and l. And then in this case you need to draw these radial functions for 1s, 2s, 2p, 3s, 3p, 3d in a same graph so that you can compare them, as well as the radial distribution function. That is the probability, the r square modulus of r square, right? And then this question you have to find the maximum probable t of r theta phi. Like you need to get the probability p of r, that expression, and then you need to differentiate with respect to r, theta and phi and make it equate it to 0 so that you can get an inflection point, right? And some more questions like why could we take a linear combination of psi2 1 plus 1, psi2 1 minus 1 to generate real atomic orbitals px, py? Why not the linear combination of 2 1 0 and 2 1 plus minus 1? What is the physical meaning behind that? We can't take a linear combination of 2 1 0 and 2 1 plus minus 1. Not only the it will not, obviously it is not going to yield you the real function, but also you need to look at from the terms of the orbital angular momentum or something like that. Okay, now another very important question from here, you can use this psi 1 and psi 2 and take a linear combination to see what kind of real orbitals can be generated, and maybe another some similar questions are there. So I will urge you to solve this question by yourself, and the next day we'll meet and we'll solve this question. For now it is almost 9, so we can stop today and we'll meet on the next day. I hope whatever we have discussed today, like the hydrogen atom, how we can reach the Schrodinger equation, I can form the Schrodinger equation, proper Schrodinger equation for the hydrogen or the hydrogenic atom. And this actually, I hope this was helpful to you and you get a better idea about the thing, and will be able to solve the numerical questions what I have provided to you. And with that we'll actually stop it today's session, and we'll meet on the next day, that is next Tuesday. Thank you for joining.